All right, so can you hear me? Welcome to once again to Web3 Aficionados blockchain development workshop. My name is Adiola Adeshino, and I'm supposed to take you the first class, um, um, blockchain fundamentals. So this class is meant to explain the fundamentals of the blockchain and break down what the blockchain really is to you. And I'm a pharmacist by choice of what I studied in school. But by choice of what I wanted to do after school, I decided to be a data scientist. I do a lot of things though, but these are very few things that I do. I also do some copywriting on the side, and then I am a community model at Web3 Aficionados. So what do we do at Web3 Aficionados? We want to solve two basic problems. The first problem is that there's a lack of sufficient coordinated knowledge about the blockchain. A lot of people do not know where to find adequate information on the blockchain. And the second problem we are trying to solve is that there's a huge barrier into Web3. So to solve the first problem, we hold space sessions on Twitter and AMAs on our Telegram groups just to help people get informed about the blockchain. And to solve the second problem, the huge entry barrier into Web3, we hold workshops for newbies to train them and help them get their first Web3 jobs. Um, so I'm using the data approach to teach blockchain for two reasons. One is that the entire blockchain information on the knowledge talks about Bitcoin a lot, but finance does not cut the entire picture, and the blockchain is bigger than Bitcoin. So I decided to use another approach to see if it's going to break down blockchain basics better than using Bitcoin as the whole approach to blockchain education. So pre-workshop activity, so we've done introductions. We would require you to use the hashtags NADOS workshop on Twitter, take screenshots. If you've learned something new, write about it on Twitter, social media, so that we can gain more visibility and help more people. Right. So we want to use big data to explain the blockchain. So we need to define what big data is. So there's small data that you might have seen if you've used Excel, right? Excel houses small data, but then there's big data. And here are the three properties of big data. Is that big data has a very huge size. So imagine yourself sitting down at, say, Google's data center, or say Amazon data center, or say Facebook data center. Imagine all that volume of data these companies have to deal with every day, right? So big data has very huge volume size, data size. And the second thing is variety. There's a lot of data companies generate on the internet. There are JPEGs, there are audio data sets, there are video data sets, there are Excel files, there are so many types of data sets, JSON files, CSV files, so many different types of data sets that these companies need to make use of. And then there's the speed at which this data comes in. Every second, data is generated on Facebook. Every second, data is generated on Twitter. Every second, Amazon generates sales data. So we look at the velocity, at the speed at which this data comes in, and these companies still need to make sense of this data, right? So we look at early data processing methods like Zookeeper at Yahoo, Big Map and MapReduce at Google, and then Cassandra as Facebook. And then more recently, we have open source distributed file systems like Hadoop distributed file system, and then Hadoop MapReduce. Now, here are the big data challenges. So what we want to do is that we want to conceptualize a challenge or a problem, and much later we look at how blockchain solves that problem. Right. So let's conceptualize a big data problem, and then later on we'll see how the blockchain solves this problem. Now, the first big data challenge is who will control the infrastructure when there are multiple players involved. So let's say I want to, again, let's say I want to predict if a flood will happen in Mumbai, India, or in New York, America, right? There are multiple players involved in fetching these data sets. I'm going to need geospatial data shared among multiple governments and private agencies. I'm going to need meteorological data. I'm going to need land usage data. I'm going to need municipal data and different kinds of data sets. So the question is that who controls the infrastructure when there are multiple players involved? Who will take charge of the data? The second question is that if there are multiple copies of this data at different locations, like I've said, how will you know which one is most up to date? How will you know if there's no hanky-panky going on somewhere? How do you know if your data set's integrity is maintained, right? So these are big data challenges that we have today. And that question is, how well can you trust the data? On your own end, if you've generated a data set yourself, how can you prove that you are the original, you are the originator of the data set, right? If other people are the ones uploading this data or generating this data, how can you prove that they are the ones actually generating? How can you prove that there is no random bot on the internet generating this data set, right? And that question is that how will you handle crash and malicious behavior during data transfer? And this is one of the very, very, very huge promises of the blockchain. And that question is that how do you monetize the data sets? How do you transfer rights of the data? How do you know who has rights to do what and who has rights not to do what? How can we develop a universal data marketplace like the electricity or the internet? So these are data challenges that we have in the 21st century that we use the blockchain to answer. So the blockchain solution for such questions is what we call blockchain DB, a blockchain-powered database. Right, so blockchain DB is a controls database infrastructure shared among entities. It could be within an enterprise, it could be within a consortium, it could be within between different countries across the planet, right? So here, infrastructure can be spread across different locations, and then the integrity and the consistency of data is ensured through the blockchain. So let's take two use cases, right? So let's say there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 companies that have decided to share data with each other. So this is our use case, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So 4-year, 4-year, 2-year. There are 10 companies who have decided to share data with each other. Each regional office with its own system admin controls one node of the overall database, right? So each regional admin or each regional office for each of the individual companies with its own system admin or its own IT office, so to say, controls one node of the overall database, such that the entire database is controlled collectively, right? So no one person has control over the database. Data is protected, is still protected, even if 1 or 2 sysadmin goes rogue or a regional office is hacked. This is the promise of the blockchain, right? The data is still protected, even if 1 or 2 system admins goes rogue or 1 regional office is hacked. That's one use case. The second use case is consider a data pipeline, for example. Let's say some IoT company that generates, let's say that an IoT company that takes the temperature of in Lagos and reports it to a dashboard, for example. So let's say I built a company and I want to monitor the temperature in Lagos State, right? So I have an IoT sensor. This is the journey via which that particular data that is generated every minute or every hour is moved from the IoT sensor to my website or my Tableau analytics dashboard. So I want to analyze the temperature in Lagos State and predict what's going to happen tomorrow or next week, right? So it's called a data pipeline. Data moves from one point to my analytics dashboard, right? So consider this data pipeline that moves from the IoT sensor to a Kafka stream, then to Hadoop storage, I've mentioned Hadoop, and then to a Spark data cleaning. All of these are data jargons that you really don't need. then to a MongoDB database, and then to Tableau Analytics, right? So consider this use case, right? So 10 different companies sharing data with each other, and each of the offices has one node or has a system admin that controls one node of the overall database. And consider a second use case, which is a data pipeline that talks about how data moves from the point of generation, the point the data is generated, to where the data can be consumed. Here it is, my Tableau Analytics. Now, before each data pipeline step starts, the input data is timestamped as follows. So I need you to write down these three things because you're going to be tested on these three things, right? A transaction is created. That transaction contains a hash of data and the metadata. A crypto transaction or a blockchain transaction contains two things: the hash of the data and the metadata. After the transaction is created, the transaction is cryptographically signed by who? By a miner. We'll get there later. The transaction is cryptographically signed. And then the third step is that the transaction is written to the blockchain database. Three very important things, right? This will timestamp the transaction. So a transaction is created, the hash of the data, note this hash down because I will explain hash much later. The hash and the metadata. Metadata just means something that describes the data. So metadata, something that describes the data. So this metadata describes the hash. So if you need more information on this hash, you can get it in the metadata, right? So after the transaction is created, the transaction is cryptographically signed, obviously by a miner in the case of Bitcoin. And this transaction is written to the So this transaction is written to the blockchain database, and then this timestamps the data. So the most important word here is the timestamp, because immediately a blockchain transaction is generated, it is timestamped on the blockchain, and it's very immutable. Immutability means that that timestamp cannot change, right? So you have immutable evidence that you had access to the data at a point of time, or that you generated the data at a point of time. Does that make sense? Now let's answer the questions now. How will you prove that you are the originator of the data? The data is cryptographically signed and stored in an immutable database, which is the blockchain. So the blockchain is immutable, such that when a transaction is generated, it cannot change. That's how you can prove that I originated this data set at this time. Second question is what about crashes and malicious behavior? So what you do in the case of crashes, you rehash the data. You obviously would not understand rehash because you don't understand hash yet, but I would explain hash much later. So you rehash the data and check the information from the blockchain. If there's a mismatch, that means something is wrong. So you keep rehashing and you keep rehashing till you find the hash. So Bitchain DB has certain features, right? So this is a blockchain, which is a database, right? So it has certain features. The first feature is decentralization. I need you to write down all of these features because you also be tested on these features. So the first feature is decentralization. That means that there's no single point of control or no single point of failure, right? So for example, 10 companies sharing data with each other means that all 10 companies are in control of the data and no single one company is in control of the data. So that's the meaning of decentralization. No one is in control and everyone is in control, right? Query. You can write and run any MongoDB query over the database from anywhere in the world, right? So once you run a transaction on blockchain, Bitchain DB, sorry, you can write any MongoDB query from anywhere in the world and query the database. It's the same way if I send you Bitcoin right now, I can query the blockchain ledger 10 years to come. It cannot change, right? So that's for query. Immutability says that once stored, data can be changed or deleted. Immutability says that once stored, data can be changed or deleted. I've explained that. Byzantine Byzantine fault tolerance says that up to 1/3 of the nodes in the network can experience arbitrary faults and will still be fine. That means that if we have 10 companies sharing data with each other, up to 3 or 4 companies going rogue means that we are still fine, right? So if there is problem with 1/3 of the nodes in the network, or if there's a problem with 1/3 of the participants in that network, we are still fine. That's what Byzantine fault tolerance means. Low latency means that transaction finality happens first. So I've explained that here. Customizable means that you can design your own private network. So if you have enough money and you have a purpose for it, you can build your own private blockchain. A lot of people do, and I've done that. So rich permissioning means that you can set permissions at different transaction levels, right? So you can set permissions at different transaction levels. You can decide what company does what. You can decide what company has the power to do what, and that decision is made collectively among all 10 companies. I hope this makes sense to you. Now, the beautiful thing about this is that every feature that BitchainDB has, Bitcoin also has, right? So let's go back. Decentralization, no single point of control, no single point of failure, is the same thing for Bitcoin, right? So Bitcoin is also a blockchain where there are thousands of nodes controlled by thousands of miners, such that no one is in control. And before a transaction can be confirmed, every node needs to confirm that transaction, such that everyone is putting eyes on what everyone is doing and no one can game the system. So that's decentralization. Query means that I can query the Bitcoin ledger at any point in time. So let me show you what that means. So let's say I want to look for the blockchain. What was it called? The Blockchain Explorer. Great. Blockchain Explorer. So I come to the Blockchain Explorer, right? I'll come here and I can paste just any crypto or Bitcoin or Ethereum wallet. So there was one I did last week. Let me look for it. So I queried someone's Bitcoin Ethereum wallet, and I was able to find. So this is Benga, I think. This is Benga's Ethereum wallet. So we can see that this address has transacted 27 times on the Ethereum blockchain. It has received a total of this Ether and sent a total of this Ether, and the current value of this address is this Ether. Right. So you can see this is the hash for this address. This is the nonce. I will explain nonce later. This address has transacted 27 times, right? This is the final balance right now, and this is the total amount of Ethereum that this address has sent. So if you scroll down, you will see all the transactions. So you sent 0.05 Ether at this point. This address receives 0.05 Ether. You can see the gas fees. You can see the hash. I'll explain all of these things later. So what I'm trying to explain here is that you can query the Bitcoin or just any blockchain. You can, once it's a public blockchain, you can query it at any point. Also, immutability. Bitcoin transactions are very immutable. The blockchain is immutable. So once I send you Bitcoin or you send me Bitcoin, the data cannot be changed or deleted. We also have Byzantine fault tolerance that Nakamoto uses. And that means that 1/3 of the nodes in the network can experience arbitrary faults. I've explained that. So all of these other features that BitchainDB has, the Bitcoin also has. Right. So let's look at how this works. So I've explained that all of these companies now, all of these 10 companies, in the case of 10 companies, in the case of 10 companies trying to share data with each other, all of these companies can be called nodes for Bitcoin, right? So when we bring the analogy back to Bitcoin, all of these guys here are called nodes. That's what I wrote here. So you understand. And another thing you need to understand is that there are people who sit down at these nodes. They are called miners. There are people who sit down at these nodes. They are called what? They are called miners. So people say that these nodes are called what? Miners. So just note that down. So as you can see from the diagram, all the nodes are interconnected. That's what I attempted to draw on my Google Arts, on my Google drawing. All these nodes are interconnected such that this guy knows what this guy is doing. This guy knows what this guy is doing. This guy knows what this guy is doing. So no one can game the system, right? So this is what the blockchain database looks like. So blockchain has three basic promises. Excuse me. The blockchain has three basic promises. The first one is decentralization. I've explained decentralization earlier. The power or control is not held by a single entity. Instead, it is distributed among multiple participants. Right? I hope this makes sense. Very self-explanatory. If one node is corrupted or fails, the network repairs itself. Right? The second promise of the blockchain is peer-to-peer. Right? So we can have or generate direct peer-to-peer transactions of data or finance. So for my example, we did peer-to-peer transaction of data. For Bitcoin, we are doing peer-to-peer transactions of money, right? Of a digital currency of finance in general, right? The centralized nature of blockchain instills trust in the process, such that two unknown parties can directly interact or transact with each other without knowing each other. So I and you watching me can transact in Bitcoin from China, from Mexico, anywhere in the world without us having to meet each other. So that's what peer-to-peer means. And distribution means that data is distributed among the nodes or among the sysadmins in the example of the 10 companies sharing data with each other. If one node is tampered or if one system admin gets tampered, the data does not get compromised. This is the promise of the blockchain. Right, so let's go into some date-time analysis. Sometime in 2018, or sorry, 2008, Satoshi Nakamoto posted the Bitcoin white paper to the forum. Much later, as we move on in this community, we'll be analyzing the Satoshi Nakamoto Bitcoin white paper. Right, that's the father of all white papers. The Bitcoin is the father of all cryptocurrencies. And in 2009, the first data block was generated in Bitcoin. So let's look at the timeline. So here we had Bitcoin, here we had Litecoin, much later we had Ripple, then we had Dogecoin, then we had Stellar, then we had Ethereum. So Bitcoin is called a peer-to-peer electronic cash system, right? Once again, it's peer-to-peer. So it's a peer-to-peer electronic cash system where I can send you Bitcoin and you can send me money from anywhere in the world, right? Again, this is how the blockchain looks like, right? All nodes or system admins are connected to each other. So every node has a full copy of the data. So here are very important lines that would help you understand the blockchain. So every node has a full copy of data means that every node knows what every node is doing. So no one is acting in isolation. This node cannot act in isolation. Every node knows what every other node is doing. New nodes appear and disappear all the time. I mean, that's a given, right? Bitcoin can decide it wants to add 100 nodes this month and add. So Bitcoin nodes, exist and appear and disappear all the time. It doesn't matter if one node decides to go down, or it doesn't matter if one node decides to join the network. You can have 100 nodes joining the network. It doesn't still matter. As far as it works on this same principle, the network is still fine, right? Every node runs the same software to verify data blocks, right? So the same software that generates the hash, which I'm going to explain later, every node runs that same software to verify the data block. Now, each node, please can you mute your mic? Each node is connected to a few other nodes only, right? So, for example, look at this diagram. This node is connected to this guy, and this guy. He is not connected to this guy and this guy. So each node is only connected to a few other nodes only. It doesn't need to be connected to everybody. It just needs to be connected to a few other nodes. and those few other nodes are connected to a few other nodes, and the system is fine. Now, and that statement is there is no trusted node, right? So in this network, we don't trust each other. That's why the miners in this node do a lot of verification and verification and verification, because we do not want to trust anybody, right? So there's no trusted node. And the goal of having these nodes interconnected is to have a single truth about the data that can be verified by everyone. So this is the goal of the blockchain: to have a single truth about data that is being generated, or to have a single truth about the Bitcoin or the Ethereum that is being sent or received, that can be verified by everyone. Right. I hope that makes sense. Again, we've defined the blockchain as a chain of data blocks, right? So a chain of data blocks. So this is a chain of nodes that generate data blocks. So blockchain is a chain of data blocks. And we've defined Bitcoin as well as a chain data containing financial transactions. So Bitcoin is a chain data containing financial transactions. In my example, BigChain DB is a chain data containing data transactions. So for example, once again, this is a chain data. This is a chain of data blocks containing data transactions, right? While Bitcoin, again, is a chain data containing financial transactions. So you can use the blockchain to solve any problem, whether it's from finance or it's from healthcare, or it's a data problem. As far as this interconnection exists between nodes, we can maintain checks and balances and make sure that the integrity of data or the financial transactions being generated are good, right? So like we've said, we want to have a single truth about the data. That's what the diagram means, right? So false data is generated, true data is generated, and then the miners try to find out what is the truth about the data set, right? So which pair should node A believe about block 4? We would analyze which pair should node A believe, because block 4, what miners do basically is that they want to find something that is called the hash value, right? So once they find the hash value, the data block is committed to the blockchain. But if they don't find that hash value, they have to keep rehashing and rehashing and rehashing till they find that hash value. I will explain in a couple of slides ahead. Now, let's talk about consensus. Let's talk about consensus, because in my example, if you have 10 companies who have decided to share data with each other, these 10 companies will need to come up with a consensus on how they want to operate, right? So this is a traditional consensus, for example, because these 10 companies know each other. They know each other's offices. So this guy can walk into this guy's office, and this guy can walk into this guy's office, right? So these guys will need to have a consensus to say, let's set permissions for, excuse me, let's set permissions for these guys to be able to do this. Let's decide how we want to generate data sets, right? So a group of people working together, right, would have to come up with their own traditional consensus, or with their own consensus to determine how they want to operate, right? So that's what we mean by traditional consensus. Historically, consensus has been analyzed in a closed setting where both participants and their identities are known to all. So that's what I just explained. Under traditional consensus, we could have two types of messaging. We have asynchronous messaging and we have synchronous messaging. Under asynchronous messaging, messages will eventually arrive, while under synchronous messaging, messages will arrive within a bounded time delay, right? So let's say synchronous messaging, the data comes in every 2 hours, right? Every 2 hours, or we've decided that every day, or let's say at 12 midnight, we want data to be committed to the block, to the chain to the network, right? So that's what we mean by synchronous. It has a bounded time delay, but in synchronous is continuous. The word in synchronous just means continuous messaging, right? So we have two main asynchronous solutions. We have Paxios and we have practical Byzantine fault tolerance, I explained earlier. So under Paxios asynchronous solution, nodes may crash, but there are no Byzantine nodes, right? So we can tolerate up to 1/2 of the nodes crashing. That's what this means. And then under Byzantine, nodes may crash, and we can tolerate up to 1/3 of the nodes crashing. So it means that once one third of the nodes crash, we are still fine. But Bitcoin or Nakamoto came with something called Nakamoto consensus, under which the Bitcoin operates, right? So Nakamoto consensus is a synchronous network, right? That's data generated every time and anytime that can, sorry, hold on. So Nakamoto consensus uses the synchronous network and can tolerate up to half, malicious miners or half of the nodes going rogue. I'm sorry. Right. We've mentioned that in traditional consensus, data commits are final. However, in Nakamoto consensus, blocks are not finalized until the hash value is found. So you can see that I've been mentioning hash value, hash function. Blocks are not finalized until the hash value is found. The hash value provides a single truth about the data set, right? Such that they can be probabilistically replaced in the future. So it means that if a miner at a particular node, right? If a miner at this node, welcome Samson. What we are doing today is what we did last week. So you can decide if you want to, and what concerns you your class will be treated on Friday. So you can decide to wait or go, but we'll see on Friday. So it means that if a miner at this particular node makes a mistake and commits a wrong makes a wrong commit, all of these other guys can cross-check what he has done, and then he can rehash to find the hash that he needs. So that's what we mean here by in traditional consensus, data commits are final, but in Nakamoto consensus, blocks are not final and they can be replaced in the future. Earlier blocks are less probable to change, and there are 10 minutes between blocks on average. The median time is 6.5 seconds, the mean time is 12 seconds. And so this is all just basics about Bitcoin consensus model. So Bitcoin solves two inherent financial problems, right? The first is authenticity, and the second is double spending. So authenticity wants to make sure that you really have the funds in your wallet, and double spending wants to make sure that if you have one Bitcoin and you send out one Bitcoin, you can't send that one Bitcoin to person A and send the same Bitcoin to person B. So we are solving two problems, authenticity and double spending. Those are two financial problems that we're solving. Authenticity is solved with encrypted signatures and showing proof of funds by miners, right? So I'll talk about that later. Confirmation of payment requires more effort. So I'll explain that. Just leave this behind. I'll explain that. I'll explain that here. Right. So this is the core of what makes the blockchain the blockchain. This is the core of what makes Bitcoin Bitcoin, which is called the proof of work. So let's explain proof of work now. Proof of work was first used in email spam detection, but Bitcoin learned the idea from hash cash currency. So for example, we can say that if this mail has 35 words, right? So we are saying that if the proof of work is not attached to spam, else count the words. If word count in proof of work is wrong, discount email as spam. So what we are saying is that we are giving this proof of work a difficulty level, and this mail has 35 words. So we are saying that, for example, if this mail has less than 50 words, right, since the nonce or the difficulty level is 50, if this mail has less than 50 words, then consider it a great message and send it to whichever email we want to send it to. But if this mail has more than 50 words, let's say it has 70 words, then then send it to the person, but put it in the spam folder, right? So it's a simple if-else statement, right? That Bitcoin learned proof of work from. But there's something else you need to note is the nonce, which is the difficulty level I've mentioned. So the difficulty level for this, or the nonce for this proof of work statement, is 50. So we are saying that if a particular email has less than 50 words, then send it to the inbox of the email. Or if the particular email has more than 50 words, then send it to spam, right? So this is just a simple if-else statement. Now, proof of work difficulty level 50, the required nonce is 15. So nonce is like a formula that you need to reach 50. So for example, this mail has 35 words, like we explained earlier. The nonce to reach 50 is 15. So this is an entire mathematical jargon that you do not need to understand, but you just need to understand that once this mail has less than 50 words, then you send it to wherever you want to send it to. Once it has less than 50, it has more, sorry, what did I say? Once it has less than 50 words, then you send it to inbox. Once it has more than 50 words, then you send it to spam. The nonce required to reach 50 is called 15. So the word nonce is important because we'll need this when we're talking to Bitcoin. We're talking about Bitcoin, right? So now, what miners basically do is that they find something called the hash, right? So let's forgo database example and think about Bitcoin now. I've explained that these nodes have certain human beings sitting inside of them, and those human beings are called miners, right? So if I want to send Bitcoin to you watching me, right? If I want to send Bitcoin to you, so here is me. I'm sending one Bitcoin worth about $20,000 to you, sitting down somewhere, wherever you are. The Bitcoin miner that sits down in this node is looking for something called the hash. Now, you don't need to understand this hash, right? Because it's an entire mathematical process to find the hash. And if we have some time, Joseph is going to teach you, if you are interested in the mathematics, we would have Joseph teaching you about hash function and how Bitcoin miners find the hash, right? So Bitcoin miners, what they are looking for is the hash value, this same hash value. So for this transaction that sent out 0.05 ether, the Bitcoin miner is looking for this hash value. Once it finds this hash value, it commits your transaction to the blockchain, and then whoever needs to receive Ethereum receives Ethereum. Whoever needs to receive Bitcoin receives Bitcoin. I want to make it as simple as possible. Oh, sorry, hold on. Right, so I want to make it as simple as possible. The proof of work is about miners spending time and effort to mine or create a block, right? The idea of proof of work is to slow down attackers, right? Because Nakamoto probably envisaged that people will come in and will try to game the system. He probably envisaged that people will come in and try to bring down the blockchain or try to cheat or try to hack Bitcoin, right? So Bitcoin uses this particular hash puzzle for proof of work, stating that we want to find the hash value that satisfies a given difficulty. So for Bitcoin, we want to find the hash value. The miner wants to find the hash value that satisfies the given difficulty. But for Bitcoin, that given difficulty is in terms of energy, right? So it has to be generated. Energy has to be expended for this hash value to be found. That's the reason why you find, that's the reason why you find Bitcoin miners complaining that their houses got burnt, or their farms got burnt, or their factories got burnt, because Bitcoin requires a lot of heat and energy to find this hash value, right? So a random person trying to hack Bitcoin will need to spend a lot of energy, right, to hack Bitcoin. At the end of the day, the amount of money and energy you spend trying to hack Bitcoin is the same amount of reward that you would have gotten hacking Bitcoin. So hacking Bitcoin doesn't make sense. Trying to hack this system doesn't make sense because you need to expend a lot of energy to find the hash value, right? So this slide just explains some mathematical principles concerning hash value. So we are saying here that once the block is mined, the miner sitting down at the node increases the nonce until a useful hash is found, right? So what we are doing is that, let's say, for example, let me go back to data. So let's say these 10 companies, what they upload are CSV files or Excel files, right? We are saying that before this guy at this node, so let's say this guy at this node wants to commit a data set to this chain, right? This guy at this node, don't forget that the guy at this node is a system admin for one company amidst these 10 companies. So let's say this guy wants to commit a data set to the chain, right? Now, numbers, we have numbers and texts. We have numbers and texts inside the Excel files, right? Now, these numbers and text inside the Excel files can be hold on. These numbers and text inside the Excel files can be defined as binary numbers, as binary, such that we can have 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, right? So for example, let's say I want to commit a particular data set into this blockchain, right? I'm going to have to convert my entire data set into binary formats. Now, binary formats has something we call zero value. I've forgotten the name, the exact name, but I think it's zero value. I'm not too sure. Zero value, right? So as the miner in this chain, I'm saying that if the zero value of this binary format is found and is greater than 10, if the zero value of this binary format is filed for this file that I want to commit to this chain, if the zero value for this binary format is greater than 10, then commit it to the chain. But if the binary value is not up to 10, keep rehashing and rehashing till you find a binary value that is greater than 10, then you can commit it to the chain. That's exactly what Bitcoin miners are doing in the Bitcoin chain, in the Bitcoin blockchain. So we are saying for nonce equals to, say, 1 to infinity, say nonce is 100 or say nonce is 1000. Nonce can be anything. Nonce is a difficulty level, right? The block hash equals to the hash, right? Bracket, the hash of the block, right? When you find the hash of this block, plus the hash of the previous block, plus the nonce, right? We find that together. If the entire block hash satisfies the difficulty level, then the block is mined successfully, right? So if this entire zero value, or if this entire text, which is converted to binary format, satisfy the zero value, for example, that is greater than 10, then mine this data or this Excel file, you can mine it to the block successfully. And then what happens is that every other system admin or every other node will verify that this data that is being committed has a zero value greater than 10, and then every other node will confirm that this is correct, and then the block is mined successfully and data is inputted into this chain. I know I'm fast, but I hope that makes sense to you. So what I'm basically trying to do is compare a data blockchain to the Bitcoin, using the data to explain what happens in Bitcoin. So the miner increases the nonce until useful block hash is found. And if such a nonce does not exist, the miner can start over by rearranging the blocks until it finds the hash that satisfies the difficulty level, right? So I hope that makes sense. So mining is a process of gathering transactions that are in the system waiting, or creating a block out of them and advertising it to other nodes, right? So I've said that a miner sits down inside the node, right? So once a transaction is generated, the miner gathers transactions in the system, creates a block out of them, and advertises it to other nodes in the system for confirmation. These are just basic informations. Creating a block is a computational review process, performing transactions, blah, 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 blah. So everyone can create transactions, but only miners can create blocks. So I can create a transaction, you from anywhere in the world can create a transaction, but only miners in the nodes can create a block. And so this is what miners basically do. They verify 4 things, right? So all of those finding hash value is just basically them verifying 4 things. They verify the source the money is coming from. So nothing is physical and the coins you spend may be fake. So the miners verify the source the money is coming from. They verify history. So even when coins are fake, you may have already spent it. So they verify your transaction history. Miners also verify users. Is the sender the real owner of these coins, and is the receiver address correct? And then the 4th thing they verify is the amount. So they verify output, inputs, and to see if those are correct. And then once all of these are correct and the hash value is found, the miners check and verify all of this. There are many nodes, like I've said, but there are few miners on the blockchain. So once again, on the blockchain explorer, there was something called fee, gas fees. So this is a reward the blockchain gives the miners for mining a block. Excuse me. So blockchain halves every 4 years. You don't need that. Transaction fee is the amount on spent from input to output. So basically, the transaction fee is the amount the blockchain rewards the blockchain miner for solving the computational problem that finds the hash value that helps the miner to approve your transaction, right? So the fee may also be 0, but why would anyone mine your transaction for a fee of 0? So the blockchain miners are doing mining for financial rewards. So for example, let's say 2 people create a blockchain transaction. One person has a reward of, let's say, Bitcoin worth $10,000, and the other person has a transaction fee of $2,000. Obviously, the blockchain miner will choose the transaction whose fee is $10,000 because they are doing it for the reward, right? So that's why your $2,000 worth of transaction fee can take up to a month to get confirmed, because blockchain miners are doing it for the incentives. So the fee may also be 0, but why would anyone mine a block for a fee of 0? So let's talk about cryptocurrencies that use proof of work. But before that, let's take questions, or let's take a break.